Hello everyone, I'm Shengwei Xu. I'm a PhD student from University of Michigan. So I'm very glad to talk about our paper, Eliciting Informative Text Evaluations with Large Models. It's a joint work with Yichi, Zhang, Schoenebeck from University of Michigan and Yuxuan, Yuqing from Peking University. So Yuxuan is my co-first author, and his author here today is our expert in coding with large models. So if you have any questions, you can ask any of us. So in our paper, we focus on how to elicit high-quality textual information. Application could be peer review. Like here is an example. Like currently, large models can generate review that looks like human, but they often lack depth and insight. So can you tell which of these reviews is generated by ChatGPT? And I will give you a little hint. Let's just focus on the critic part. So who thinks the right one is generated by ChatGPT? Okay, who thinks the left one is generated by ChatGPT? Okay, so the answer is the right one is generated by ChatGPT 4.0, and the left one is from our reviewer B. And we can see that the ChatGPT review has a very general critique that eliciting, it's like challenging in real-world settings. It can be applied to maybe 99% of research papers. But our reviewer B gives a more specific and a detailed critique to our paper. And thanks for our reviewer B's critique. And so as authors and conferences, we all want high-quality reviews like the left one, but we don't want the generic GPT reviews like the right one. So also our reviewer A also emphasized that it's very important to address the misuse of generative models in peer review process. So in our paper, our research question is, can we develop automated mechanisms to incentivize high-quality informative textual evaluations by rewarding it more than generic and low-quality content? So I want to highlight that we want to reward for the information rather than just propose some GPT detector. So if someday that GPT can outperform our human reviewers, I think most of us will be happy to use that. But unfortunately, it still cannot until now, for now. So in addition to academic peer review, textual evaluation is also important on online business reviews, peer gradings, where students grade each other's homework and surveys. So the challenge is that agents can be strategic in exerting effort and reporting. For example, people can be lazy to acquire the information. So the information elicitation goal is that we want the agents to exert effort to acquire the informative signal and truthfully report their signals. In addition, subjective information is more challenging because it's very hard to verify and there's no ground truth. So there's a need for some well-designed incentive mechanisms to elicit high-quality information. Ideally, with a mechanism, the mechanism will assign high scores to high-quality reports and assign low scores to low-quality reports. And assuming that the agents aim to maximize their scores, the score gap provides the incentive for high-quality reports. So in our paper, we propose two mechanisms, the GPPM and GSPPM. To our best knowledge, they are the first mechanisms to elicit high-quality textual reports. And we show that theoretically, with our mechanism, exerting effort and report truthfully is an approximate Nash equilibrium under certain strong assumptions. And empirically, we find that higher quality reports lead to significantly higher scores with real data. So I'd like to mention a concurrent and independent work by Ivan and Jason Hartline. They also study some score rules for textual information elicitation in a relatively objective and verifiable setting, which is different from ours. So let's come back to our paper. Here are some highlights in our empirical results. So we randomly select 300 papers and about 900 corresponding human reviews in iClear 2020, which is a top-tier machine learning conference. We use GPT 3.5 and GPT-4 to create fake reviews to these papers. And we find that our mechanisms assign high scores to the original human reviews and low scores to the fictitious GPT-generated reviews. So we observe a significant score difference between these two reviews. So in practice, specifically, we use the pair t-test to test whether the score difference between human written review and GPT-generated review is significantly greater than 0. So we use the minus log p-value as a metric for significance instead of the p-value, because here, higher value means more significant, which is great for comparison and visualization. So here is the visualization of our report. So in both figures, the x-axis is our mechanisms, and the y-axis is a minus log p-value, which higher is more significant. And on your left figure, it shows the significance differentiating GPT 3.5 generative review versus human review. And on the right figure, it shows the significance differentiating GPT-4 generative review versus human review. And we can see that both of our mechanisms has a higher significance than the yellow line. And we can also observe that the GPT-4 review in the left figure lead to a more significant score loss than GPT-4 generative review by comparing these two figures. So that implies that our mechanism can actually differentiate 3 quality levels. From high to low, they are human written review, GPT-4 review, and GPT-3 generative review. So in addition, we also find that the GSPPM has a higher significance score, and we will discuss that later. Okay, so now I will talk about some previous mechanisms eliciting subjective information in multiple choice or numerical tasks. So first, I'd like to begin with original peer prediction mechanism. So it scores an agent based on how her report predicts her peer's report. So which is the probability of HG, that's peer's J's report, conditioning on agent's I's report, Xi, and then we take a log 2 as the score of agent I, and you can use any purpose formulas here. So why this could work? So let me provide some intuition. If we take the expectation score of agents I in peer prediction, it's actually some minus conditional entropy, and we can write that as mutual information between two agents' report minus some constant from agent's I's review. So if the agent's I want to maximize her score, she will like to provide the most informative report and to maximize this mutual information. So therefore, with this mechanism, exerting effort and truthfully report is a Nash equilibrium. However, there's a strong assumption that because we want to compute this conditional distribution, we need to assume some knowledge of the common prior, and this assumption could be very strong in some certain settings. So how to mitigate this strong assumption and be prior independent? Some previous works propose the multi-task setting where they learn this correlation and distribution between reports with multiple tasks. And another approach follows an independent work, which is called Beijing theorem. So they directly elicit the prediction from the agents, and they reward the agents for both the informativeness of their signal and the accuracy of their prediction. So, however, all these existing methods are not practical for eliciting textual information. Because the signal space of textual information is too large, we cannot elicit from agents or learn from learn from multiple tasks. So can we find some practical method to elicit textual information? So let's see this example. Given these two reviews, two multiple choice reviews, can you tell which review is more informative? We can, right? So what about this, like textual reviews? So it's obvious, right? So we find that though multiple choice questions have a small finite signal space, it's very easy for theoretical analysis, but it will need more samples to identify high quality reports. But the text review, in contrast, it has richer information in a single response. So combining this richer information in text review and the rise of current large language models, we can use large language model to analyze the structure of textual responses. So therefore, we propose our generative peer prediction mechanism. So similar to the original peer prediction mechanism, we still reward agent's I on how her textual reports predicts her peer's report. However, here we use large language model to estimate this distribution. So we find that instead we pair with a strong GPT and a strong large language model and the richer information in text, we can mitigate the assumption of knowing the common prior, and we can inherit the very nice theoretical property from the peer prediction mechanism. So here is our main theorem. So when the large language model can provide a good estimation of the underlying distribution, we find that with our mechanisms, exerting effort and reporting truthfully is an approximate Nash equilibrium. Okay, so here comes the quick question: that how to estimate this distribution with large language models?
Isn't exerting low effort also a Nash equilibrium though?
That's a great question. Actually, it's not. So like in our paper, we model three like effort levels: no effort, low effort, and high effort, and we show that exerting high effort is a Nash equilibrium. Oh, wait 1 minute. So okay, so I think if both of the agents exert low effort, that could be a Nash equilibrium. But we will discuss that later. We propose the generative synopsis pure prediction mechanism to solve this problem. Sorry for the confusion. So we propose two implementations to compute this prediction. So as you may know that generally large language models work by predicting the next token. So we propose this implementation called token by predicting by the log probe of next token. For example, given the prefix eliciting informative text, the large language model can generate a distribution over all possible next tokens. And we can get the probability of next token equals to evaluation given this prefix. And we can do this step by step. So given some prompt, and we can first predict the probability of first token equals to eliciting. And then we predict the second token equals to informative given the prefix and the prompt. And we can do this step by step. So we get the probability of all the tokens, and we multiply this together. So with Bayesian rule, we have the probability of the whole sentence given this prompt. So how to estimate this conditional distribution? We just integrate xi, which is agent's ice report, into the prompt, and then force the large language model to generate agent's JIS report. And we use the probability of generating agent's JIS report as an estimation of this conditional distribution. Okay, so that's our first mechanism. First implementation. But to access the token probability, we need to have the access to the output layer of the neural network, which is only accessible with open source large language models. For example, Llama 2, Llama 3, or Mixture. It's currently accessible with most commercial APIs like GPT and Cloud. So we propose an alternative heuristic method called judgment. We use large language model as an oracle, and we first split the report into several independent judgments, and then we predict the probability of each judgment with natural language, and then we multiply that together. So I will skip the details due to the time limit, but we provide that in our paper. So at the end, I will talk about some practice insights. So we know that in practice, the textual responses are high dimensional. It could include some semantics, language styles, vocabulary use, and some other superficial information. In tasks like peer review, we focus on the semantics quality rather than the rest of them. So the semantics is the intended information. However, all this information could influence the large language model prediction. And the rest of them, we call that shortcut information because they are not important, but they may confound the large language model prediction. So how to filter out this shortcut information? So the first method we propose is pre-processing. So we use the large language model to rephrase the textual response into a preset format to standardize language style and remove superficial information. So it's very straightforward, but it's very effective because you can see that without pre-processing, which is showing in the light blue bar, our mechanism cannot differentiate GPT generative review and human reviews. So another method to filter out shortcut information is conditioning out a synopsis, which actually answers your question. Yeah. So here, when there's some commonly known synopsis of the item, for example, the abstract of the paper, the agents may exert low effort and construct some localized report solely based on this synopsis. And we want to reward the information beyond this synopsis by conditioning out this synopsis. So the score of agents I in GSPPM is the probability of xj given xi and the synopsis sigma. So why this could work? So I will still use mutual information to explain that. So in GSPPM, the expected score is actually can be written as some mutual information between XI and agent's X report and agent's J's report, conditioning on this synopsis minus some constant. So that means we only reward for the information beyond this synopsis by conditioning out this synopsis. So now, like the low effort, it just gives you 0. Like if we assume that your low effort signal only depends on the synopsis. Okay, so that actually explains why GSPPM has a higher significance in penalizing large language model generated reviews. Because you may know that large language model is good at summarizing paper, but they're not good at like provide useful and insightful like judgments. So by conditioning out this synopsis, so we reduce the mutual information contributed by the content of the paper, but we keep the mutual information contributed by the judgment, which is the high quality information of the paper. So that's why GSPPM has a higher significance. So I have some actual empirical results, but due to the time limit, I will skip that, and you can find that in our paper. Okay, so in conclusion, in our paper, we propose 2 mechanisms, GPPM and GSPPM. They reward agents for the information amount in their textual response reports. And we propose 2 implementations, token and judgment, to get the larger model prediction. So combining one mechanism and one implementation, we can put that into application. So we have some results here. The first is theoretically, we show that exerting high effort and report truthfully is an approximate Nash equilibrium. And we find that empirically, higher quality reports lead to significantly higher scores in experiment using iClear and the Yelp review dataset. Okay, so there's some revisit of our findings in our experiment. So like we already see this before. So in the future, there's several future directions. First, in our paper, we mainly studied how to make the agents how to elicit the mutual information. How to elicit high quality information, which we focus on the X-ante score. But it's also important to study how to evaluate the agent textual response, which is the ex-post score. Also, we'd like to study how to generalize our method of large language model prediction to more mechanisms, including the multitask peer prediction and Bayesian truth theorem. So we also want to test our mechanism with more sophisticated manipulation strategies and test more properties of our mechanism, including fairness and efficiency. So thanks for listening. Here's the QR code for our paper on ICAP, and we will keep updating that, but there won't be a major change. Yeah.
I have a simple technical question. So you're computing a score, right? Token
Yes.
by token. So
Yes.
control the length of sequence, because you have more tokens, you multiply more numbers smaller than 1.
That's a great question. Thank you. So I want to highlight that. So when we compute the score, we actually compute the score of agents G's how agent's I's report predicts agent's J's report. So agent's J's report is fixed. Like if you change your length of your report, it won't change your peer's report length. So that's fixed. So you can only change XI. That's agent's I's report, but agent's J's report is a kind of a constant. So the length won't affect the probability.
So do you have any guarantees on the budget of rewards? Because if there is no upper bound on rewards, we can just scale the peer prediction reward high enough, and then the effort cost will be negligible.
Okay, that's a great question. So actually, we have 2 posters about that in this conference, and one is high effort crowd by Yichi Zhang, and one is called sport check equivalence by me, and we can talk about that later. So we just rescale that maybe by some tournament or by some method. Yeah, so that's a good question.